Okay, ballistic pendulum report. We kind of went over all this stuff in class. Maybe not as a coherent, do this, do that. So, of course, the title is rather obvious, I suppose. Well, let's just keep it simple. Okay, so we report on a device called a ballistic pendulum. We will show how the the device depends or device uses the conservation, the laws, I suppose, of conservation of momentum and conservation of mechanical energy to measure the speed of a projectile. So then let's see, so we need some background. So I need a brief history. Then you describe it in the general terms. You have a block or of some sort on a swinging pivot. And then a bullet is fired into the block. And the bullet sticks. And the block swings. And the bullet speed is determined using the mass of the bullet and the angle of max swing. So what's up to you now? So I would make a detailed drawing of those things. And somehow And then, of course, you know, you want to relate perhaps the angle with this height. That's up to you. So, let's see, how could we start out with this? So, right, so you might start in by saying conservation of mechanical energy of a pendulum. So you discuss these two positions at theta equals 0 and at theta equals plus minus max. And there's the idea of PE and KE. Of course, you then have to talk about gravity as a conservative force. So then you say, well, you know, if theta max is a data point, this means that we know the PE there, and this means that now if we know that, we know the KE at theta equals 0. And so that at theta equals 0, the KE is going to equal to the 1/2 the total mass times the V squared. I guess I left something out here. Of course, we need to know the mass of the block. So what can we do with this information of the V squared, with this V? So that's the total. It's not the speed of the bullet. So then you say, well, the bullet striking, or the bullet impacting with the block is a collision, and in fact it is a special kind. It's a totally inelastic because they stick. So then you have to say, okay, collision is two objects striking, something like this, and no outside forces. And so we also then know that this is why you can't use conservation of momentum on a pendulum, because there's an outside force. So then there's two laws that govern the collisions. You know, there's momentum and mechanical energy. And in this case, it's only KE because there's no PE. There's no outside force. And then you say, well, look, momentum is always obeyed. So then you draw out you have the momentum equation for the bullet and block collision. And then the KE equation. Now they don't equal each other, but you show the derivation where you can plug in the V final from momentum into the KE final of the block and the bullet. And I leave that to you to dig through your notes to get all that. So then now you say, look, we using all these principles, then we can solve for solve for the momentum, the speed of the bullet, V bullet. And so that you say, okay, the KE final of the collision equals to the KE of the initial of the pendulum. So there's letter things, right? There's the mass total, V total, and there's the mass total and V total in here. But also you can substitute in the V final from momentum. You can have an expression for the V bullet. So you can get that this V final of the collision with as a function with among other things the V bullet. So at the end of the day, you can have an equation that says that has here V bullet and everything on this side would be the mass of the block, the mass of the bullet. We did this. The mass of the bullet, and the height. So that's the mg delta, the mgh, because you can get rid of the theta, the angle. Originally, remember you started out with the angle, but you can get an expression for h as a function. H is a function of theta, so you can get rid of the angle. You can, or at least no, you don't get rid of the angle. What you do is you're plugging in theta because you measure it. So you're going to have, at some point, with all these steps, you're going to have an equation with the velocity of the speed of the bullet, and all you have to do is plug in the mass of the bullet, the mass of the block, the theta, so the height, the theta, the angle, and I think that's it. Yep, so you have to derive that. Then, well, you don't have to. It should be in your notes. We did it in class. So then the next thing is your procedure. So then we had the sim, the sim number 1 or whatever we called it. That I believe it's the BU sim. Let me pause this for a minute. So you didn't see any time lag there. So we had this sim here, and we had our equation. So we verified our equation with this sim. So if I was you, I would set these parameters, and I guess in this case you want to take your you have the equation we talked about here, but now you want to make an equation for theta equals all these parameters. And then you say, look, we set these parameters, then we predict the angle should be this. And we went ahead and ran the simulation, and we confirmed that it works. Maybe you've done it more than once. And let's see, this is, now this is the, actually a little bit, this procedure here is the, for so-called data taking. So this is just still the sort of like, this is not background anymore. This is testing your formula. These are just notes from class. And then once we, so let's just write this, notes from previous class. Okay, so then here we use this sim to test our equation. Well, of course, again, the equation I said was with velocity equals. In this case, it's theta equals. And then we went on to use this other sim, the GeoGebra, I guess. I don't know how to pronounce that stupid word. Let's see, cut, paste, and remember, don't go into lots of detail. Just say this. In fact, there you go. There, it's right there. Very simple. Let's see, where did it go? Huh. Oh, right there. I'm looking for it. It's different tabs here. So there it is, GeoGebra. And so I'll snip this new one. And GeoGebra. And then we did 3 runs. We set the parameters each time. And in this case, we're just measuring the height, but you can relate that to theta. And then, so then what we did is we also just cut and paste. This just makes it, I can make it smaller, it makes the file smaller too. So we calculated with our equation each time what the height should be, and then we ran the sim to see what it ends up being. And so let's see, what kind of data table would you make? We have, I thought I wrote it out somewhere. We have 1, 2, 3, 4. Right, and then we have there's three parameters, I suppose. Right, of course, uh, mass of the bullet, mass of the block. Now we don't know the speed of the bullet. And that's something, but we changed the initial speed, it's unknown. And let's see, we get the height. So then this is measured height. So then we can have the V, give me a minute. Yes, the V predicted by our model, by your equation. And then this thing here, I guess, tells you right away. Yeah. What your, so there's no, so that's your V measured. And so it doesn't, I don't know if it's going to tell us our V actual, but it will tell you the percent difference. So you don't have to actually calculate it. All right, so then in principle, it's going to be little or no percent difference each time. You have a little bit of error with, it's a little tricky measuring that height. I'm not going to have you do the error propagation. And then you know, there's not much in the way of conclusion, or because it's not real, but you can make a statement like a concluding statement that we have described the apparatus, we described the principles, and we tested, and using them we derived equations, and we tested them basically two different ways, if you will. And we've now done, if everything works, then we have a proof of principle. So all we can say is that it looks like that if we built one of these things, it would work. And there you go. So it's pretty straightforward, because this is a lab really that it's hard to do it without having the apparatus. And the apparatus is pretty clever, actually. But you know, we still have the opportunity to learn something. Okay, so this is going up to YouTube, and I'll post these slides also.